all the way, at least with the methods that I currently have in here. It freaking works. Seems to, anyway. I'll still have to build a visualization, like particle system around it like I did for the other one, but this is really cool, and it's fast as hell. Like, comparatively, it's so much faster doing it in C++ than it was doing it the way that I was doing it. I mean, I was still multi-threading it the other way, but this is actually bananas. It does have some restrictions. If you put too many points in, you can hit out of memory issues. I don't know if I'll hit it on 200K, but let's try it. So I run, come on, 200, 200, 200, 200, 200, 200, 200, 200, 200. There it is. Inserted 2 million nodes actually. Probably fully saturated the tree to the depth that we were looking in. And we can look. These are older logs. We can see that we iterate through inserting 200,001 nodes in each point. It's only because I did the loop starting with 0. We're fully populated at depth 1. Fully populated at depth 2. Let's see. Not actually fully populated at depth 2. Actually. Is that right? Oh, is it actually cubed? I guess it would be, huh? No. Wrong. Each cube divides into 8 subcubes. Anyway, I gotta do the math on this shit, but 272 at 3, 1160 at 4. Yeah, so it's times 4 each time. That explains it. So, is that right? Now, level 1, level 0 has 1 node. Level 1 has 8 nodes. Level 2 has each of the 8 nodes breaks into 8 more nodes, so 64. Yeah, that's it. And then finally, this is the sum total of all the nodes. So there's overlaps here. There are collisions. I'm using a point clustering algorithm instead of storing an array of inserted points this time. And that's why there's less nodes total than there were inserted, because it's colliding, because I'm inserting massive numbers of points. So it's not terribly surprising that it would collide. And you can figure out the number of collisions by the number of points minus the number of points found. So like here, at depth 10, inserting 200,000, we had roughly 5,500 collisions. But yeah, and it's fast. I mean, we just watched it do 2 million points in like less than 10 seconds. 1,000, 2,000. It has to build that. Okay, 1,000, 2,000, 3,000, 4,000, 5,000, 6,000, 7,000, 8,000, 9,000, 10,000. So in about 10 seconds, it inserted 2 million, did 2 million tree inserts and fed back 1, 2, 3, 10 find at depths and 1 find in depth. So 10 layer finds and 1 like difference between find at depth and find in depth is find at depth is targeted at a specific layer, whereas find in depth is all it's inclusive of all the sub layers. So you get all the nodes from all the other layers that are in between the node and the depth that you're searching. At least with the way that I currently have it implemented. So I haven't obviously rigged up any graphics or anything to this yet. It's just in this kind of test harness project that I built. But the cool thing about this is it's a plugin, so I should now be able to package this plugin and put it in my main project. So that's coming up. And then I want to start using this sucker to do some cool shit. I think I still need to write like a neighbor search algorithm. I'll have to think about that because I'm not sure what that's going to end up looking like completely. But yeah, I just thought I would show this off real quick. I'm pretty happy. It took me a long time to kind of hammer out a lot of the multi-threading behavior. And I ended up using promises. So let's take a look. Here's my async wrapper implementations. When I was debugging, I wanted more fine-grained control over when I start the thread. And so they have a start method that I added to actually assign them to a thread and dispatch them. These extend a... Let's take a look. These extend f-runnable. Implement all the methods, obviously. And then the frame that I'm actually running them in is in the wrapper itself. Right here. So we can take a look at the async book insert method. We're basically defining some values here because sometimes I do recursive changes on the actual values I'm using, and I want to be able to return the final packaged result. We're modifying the tree in place instead of copying it like we were. We don't have to do that anymore because we have proper reader-writer locks in place now, meaning that because we're synchronized... Okay, so one of the most expensive things you can do is to copy something or allocate memory, basically. Is very expensive as far as, like, computationally. It takes a relative... Like, it's fast. It's a computer. But it's relatively long compared to just, like, math. So, in order to get these kind of, like, performance gains, because if before it would take me about 10 seconds to do 100,000 nodes. And now it takes me 10 seconds to do 2 million nodes. And a big part of that is that I'm no longer cloning the tree to pass it off to a async function and have it modify said tree and then pass it back and then have to basically swap the pointer from the former node that it was to the newly updated node. I don't have to do that anymore, because I'm just straight up modifying the tree in place. And the reason I'm able to do that, if I can find it, is in these async functions. We're using locks correctly, hopefully. I mean, they seem to be correct. I've done a bunch of testing on this at this point. Firing back-to-back calls to these functions in a for loop right now, which will definitely break it if it's not locked properly. Because that's like the for loop doesn't have any, there's no way to delay it or anything like that. It just goes. And it seems to be working, so I'm pretty happy with it. So like, yeah, basically we declare a writer lock here. There's a little bit more to it. You have to also declare the lock in the header file and use it. So like over here, you can see that we declare outside of the scope of all the functions that we're dealing with. All the functions use the same block, and we just, before we're about to do our thing, which would be like this step here, for example, we lock it. I need to try, like, hang on. Let's save everything. I need to try, because it should theoretically be faster to do it this way instead of assigning a result variable. And I think my other ones, but I'm not sure if this was like vital to it working or not. Could be that I do this and I just get a bunch of fucking null pointers, but should be able to find out pretty quickly. Basically trying to avoid creating additional assignments if possible. So there's still a little bit of code cleanup here. I still need some nearest neighbor methods, but my nearest neighbor calculations would be a little bit more complicated than just the default nearest neighbor that you would normally see, because I need to check specific layers at different specific layers at different definitions of distances. So like if I'm checking in layer 1, well, you wouldn't even do that, but if I'm checking in like layer 3, the nearest neighbors will be much further away than if I'm checking at layer 55, because you get smaller as you go down, right? So with that understanding, we know that I don't need to just nearest neighbor search at level 55. I'm gonna have galaxies at like level 10, and then I'm gonna have galactic clusters at like level 10, and then I'm gonna have galaxies at level, let's say 20, and then I'm going to have stellar clusters at, say, level 30, and I'm going to have star systems at level 40. I'm going to have planets at level 50, that kind of shit. And for me to do this correctly, I will need to basically do nearest neighbor searches on all of those different levels simultaneously to get all of the relevant objects that are nearby that need to actually be populated with data. And that's just something that I haven't quite planned or mapped out in my head yet, but let's see if it works with the changes I just made. This stall here is also not a big deal. The stall is caused, I'll actually go show it. And I noticed that it actually gets slower as you get deeper because it has to traverse the tree more, right? Uh-oh. Yeah, so maybe I did do it for a reason. There was also some weirdness where, like, it was, I don't know exactly what was causing it. It was invoking the method twice when I called it from Blueprint. And I had a suspicion it was because I had methods named the same thing. Stop, we're just going to recompile. And then it happened again. I changed the name of the method, and it stopped happening. And work like that for a little bit. So I really hope it doesn't come back here, because then I'm going to be truly baffled. But basically I would call the method from the blueprint and it would invoke it twice. And then I changed the name of it to something that wasn't sharing a name with another function, and it only invoked it once. But then I rebuilt it a while ago after doing some changes, which I could have fucked up something. And it was back to invoking it twice, even with a different name. And I renamed it back to the old name, and it's still invoking twice. And then I renamed it back to the new name that I used, and it stopped invoking twice. I'm honestly at a loss for that. Like, I have no fucking clue why it was doing that. But I have one saved that was working. So hopefully it will still work when I'm done right here. With these changes. I'm not sure I trust this error. I don't really trust the runtime compilation shit seems to have caused me more problems than it has solved them. I've just mostly been recompiling when I make changes. This isn't going to be a long one tonight. I've actually been grinding on this fucking debugging this shit off stream for a bit and just kind of taking it easy tonight. This weekend should be interesting though, because this weekend I'm going to integrate this plugin that I just wrote into my other project and try getting some visualization rigged up to it, manipulating it and things like that, trying to do the same kind of things that I was doing for generating on the Blueprint version. And then maybe also look into some like nearest neighbor ideas as well. Some search function type ideas. So like I have the basic idea, like you get your center point of wherever you want to search from. In this case it would be the player's world location. You offset it by however much your universe is offset by, because remember we offset the universe to traverse to new places, because you need to be like somewhat reasonably close to the 0 axis to maintain precision of motion. So you take the user's position, you offset it, and then you have to, at the depths that you want to search, calculate some number of points. I think it's 27 gets you all the nearest neighbor cubes that are spaced out from the original point by the width of the nodes it's inserting into. That will allow me to find all the nearest neighbors for a given thing. And it could just be something as simple as like we investigate our nearest neighbors from galaxy down, and any galaxies within that range get populated. And then like the same thing, like all the way down the tree basically. Like, okay, and now what about at a smaller level? Okay, well, here's a stellar cluster I'm inside of. What are its nearest neighbors? Okay, well, these stellar clusters will be populated, but nothing else will. And then you go down again, and okay, well, now we're star systems. And you just keep doing that based on the user's location and seeking out the nearest neighbor information. Of course, you also have to populate those nodes. Of course. All right. Let's see if it was truly a null pointer. So, like, it is possible that holding the reference to the result is actually avoiding a null pointer, which is why when I was debugging it, I did that. Let's go. 200, 200, 200, 200, 200, 200, 200, 200, 200, and I mean, it seems like it worked. Found, so we did 2 million inserts, but only inserted 600,000 nodes total, which makes sense because if I insert 2 million points into a layer that has 8 members, like the direct children of the root, then the vast majority of those inserts are going to be collisions. And if I insert them in a layer that's at like 60 levels down in the tree, then there'll probably be no collisions. Just going to kind of beat it up a little bit. And this big lag spike here is not actually the algorithm. The algorithm's running while I'm playing. Like this shit's all multi-threaded, correct? Oop, there it is. Okay. Cool with that. I'm fine with, it was working fine the other way, so I'm fine with going back to it. I just wanted to see, because like when I was debugging this shit, I was kind of just throwing everything at the wall to see what would stick. And so the reason I go in here and I strip out stuff like this is because I did this like on a whim, like, oh, maybe this will fix it, you know? And I want to know if it actually helped. And it seems like it did. And I think what may have happened is that, like, basically we just immediately lose context on the result as soon as the promise fires. I'm getting better at C++ pretty rapidly, which was expected. Like, it's always that way with coding languages for me. Pick them up quickly, which is funny because I can't pick up English languages for shit. Or not English, but English is a terrible way to... I can't pick up, like, actual human languages very well at all. I suck at it. But I can pick up coding languages pretty easily. So I do want to do the thing that I do at work as well, which is when I'm finally think that I'm done with something, I will make a pass through this. I'll probably do this tomorrow on stream. I make a pass through whatever I just wrote, like line by line, like verify every single line of code just meticulously one time. Every class. I'll probably do the headers and then look at the implementations or something like that. Alright, let's try it. Here we go. And honestly, 200,000 points is overkill for the way I would be using this. It's unlikely I would ever be adding more than like 50,000 points at a time. Okay, so we got one run. Let's try it again. There we go. It works. We got no null pointers. Do it again. And I realize that if you don't actually understand what's going on here, it's not terribly impressive. Just understand that we basically, in the time span of this running, generated and retrieved... Well, we generate is the wrong word because we're doing the point clustering. So it's not like every insert necessarily actually adds a node to the system. If it overlaps with the node that's already in the system, it does some calculations to basically merge the values in a way that makes logical sense. But we're basically doing 2 million, roughly, it's not quite that, but 2 million inserts into an octree, starting at level 1, ending at level 10, and then retrieving each layer that we inserted, and then retrieving all the values in, you know, while maintaining good frame rates. This should easily be sufficient for game use. I finally can hopefully stop iterating on this Proctree because, like, we built it once synchronously, we built it again with a better data model, we built it to a point of having the insert methods with a flat structure in a hash table. That one was too slow. So we built it with throttling because we didn't want to go like full multi-threaded because that just felt like overkill at the time, but the throttling was too slow. So I built it in Blueprint with a asynchronous plugin. Oh, that's the other thing that's cool. I can ditch the async plugin now, and I can move the project to 5.2, which is great. And then finally, after I built it with the async blueprint plugin and realized that it was never going to work because it needed recursion and there were no data types to support it in blueprints that were not U objects, which are not safe to create off the game thread. Finally, I went and I did it right in C++, but I had to learn C++ to do it. So, you know, it was an effort, an undertaking, if you will. The the key here, the way we get around the idea that like, oh, can't generate U objects on the game thread, off the game thread. It's dangerous. It causes crashes. We basically create a adapter layer, which would be this guy right here. This is called a Proctree node wrapper, and this guy has a bunch of methods for accessing data, and it contains a private node of a non-U object type in C++ types so that we can have recursion in our struct, which we couldn't do that in UE5 with the UE5 struct type. The Proctree node looks like this. At least this is the definition of it. You got your parent, you got your children, you got your node data. The node data is a UE5 struct because we want to be able to inspect the node data from UE5. And basically this node wrapper here wraps a node, provides accessors to the UE5 available information of that node, and provides its inheritance, being able to basically wrap the internal wrappers when you call get child, get children, get parent, etc. So this, we've kind of got the best of both worlds. When we need to return data to Unreal 5, we can take whatever our tree data state is and wrap it in one of these and pass it back up, and you'll be able to access all the data and do whatever you need to do from UE5. But when we need to do multi-threading, we can simply pass off the core that is not a U object critically to a different thread to modify. And with proper synchronization structures in place, you can lock and unlock it in such a way that it's thread safe, and basically you get incredibly fast generation of procedural data with alongside the ability to still interface with this thing in a blueprint. This is the goal of this entire plugin that I've been writing, because I got tired of like having halfway things that worked halfway but had caveats, and I'm pretty happy with it at this point. And then the other thing that we've got is this guy. This is a Proctree wrapper. What's the difference between this and a Proctree node wrapper? Well, it turns out not too much. Because the Proctree node is a recursive structure, it basically is the definition of a tree, assuming you're holding the root or a node with a reference to the root, which would be any node in the tree. So this is a wrapper specifically around the root node of a tree that gives you an accessor to get the root, the ability to initialize the root with a size multiplier and a max depth, which is how we define our bounds of our Proctree. It contains the lock that we're going to use for, I may actually not need that. I'm going to have to look at it. But it contains a lock. I'm not sure if I'm actually still using this. At one point I tried to put locking out here. I think the locking is actually in the async functions now. But anyway, I'll check it, and if I'm not using it, I'll delete it. It has some default values. And the idea of this guy is he is what is providing us with our accessors to our async insertion functions and the root node. If I go over here, tree lock. Okay, great. So yeah, it looks like the only references are inside the file, so it should be safe to delete that. This is what I mean by like the code cleanup too. Oh god. Oh, okay, it's fine. These macros bug out. Like the... Man, I was actually kind of astounded that the IDE tooling just out of the box is so bad for game dev, and it's really a pain in the ass. Like it doesn't recognize, like the syntax doesn't recognize certain things until you build it. It's just it's rough. You're struggling against like, is this a real error or is this just basically LSP messing up? Yeah, build success. And these will go back in a second after it realizes that they're fine. So we get rid of the tree lock here because we weren't using it. We were actually using the tree lock in our async class, which makes more sense anyway, because if we're interfacing with the tree synchronously in the main thread, it doesn't need to be locked anyway. It really only needs to be locked if we are, well, I'll think about that. And it's gonna come in like, the thing is, you really don't do that except in testing, in practice. The whole idea of this tree, of this data structure, is you want to be able to interact with it asynchronously in like large operations, like things that would like basically chug the game down if you did them on the main thread. And so like inserting like single nodes and shit is not something you're generally going to be doing. It's more like you would grab the tree and go, oh, I need to put this cloud in this layer. I need to put this. I need, give me all the nodes near the player. Give me that are activated, things like that. And those are all like expensive operations. Should be multi-threaded. I'm thinking about like at least one operation that is simple, which would be finding the player's node, the player's leaf node in the tree, like, or not the player, like giving a location in the world space and having it give me back whatever the deepest leaf node occupied by that location. Now that is not expensive, but it will probably have to be thread safe, because the tree can be modified in real time. So like if you were in, like, I'm envisioning a scenario where you entering that leaf node triggers a bunch of fucking bulk inserts in that leaf node to generate like stuff, and then you just on the next frame or after a delay or something, you try to get the player's leaf node in the tree again. It's not locked. You're diving through the tree, recursing to get the node, and then the tree changes. That would be an issue. So yeah, certain methods need to be basically locked with a proper lock, even if they're not going to be executed asynchronously. Like you could run that from the game thread. It just needs to obey the same lock as all the other shit. Which shouldn't be too bad. It'll just go in the async nodes, or the async tasks over here, just like everything else. So I have get near, and it won't even be actually a take you back. I'm overcomplicating it. We really just want a nearest neighbor search that has like some custom parameters, and one of the parameters can be the location that we want to search from. That's all we need for the player's location, so it should work. There's the parameters you, so like there's there's a fun concept that arises here too with travel speeds. Say you have a node and it's about as big as the Earth, but you're traveling at a speed that is like, would be like equivalent to traveling between galaxies. Well, if you're traveling between galaxies, the Earth is an atom. It's nothing. You cover thousands of that distance in a single second. So there's some form of calculation that has to be done in the LOD, basically, to only do these calculations for layers like under a certain threshold of a ratio to your actual movement speed. I think it's log 2n is probably what it would be, because that's how you calculate the the like root node size of the tree. So it's probably, you would basically take log2 of your movement speed, and that would like per second, and that would give you the layer at which you are traversing a node in a single second. And then anything under that you could just ignore until the speed slows down. And you could do that like a polling thread or something, like every 1/10 of a second we check the player's location and speed when we do a nearest neighbors on that, but we only go down to the depth that corresponds to like whatever layer the log2 of their speed would be. And then if they slow back down, stuff around them starts loading in again, because their threshold is like increasing the resolution of the things that can load in. That's my kind of mind's eye of the way it'll all work. I don't know for sure if it'll end up working that way, but yeah, this is great stuff. Shout out to that async video I watched. It was literally from I think it's Natsu, the programmer. Doesn't have a ton of views, but it was extremely helpful. It was the best. I did a bunch of research on async. It's kind of how I work. Like if I'm trying to do a thing, I don't know how to do it, I pull in like stuff from everywhere, and I look at stuff and I throw it away, and I look at other stuff and I throw it away, and I look at something and I might keep like one thing from it, I look at something else and I might keep like 2 or 3 things from it, and then eventually you're like, okay, now I have the component ideas in place, so now I can go implement it. But that was the most helpful of any of the resources I saw on async for this. It's just like simple and intuitive. Guess I could just start code reviewing now, huh? This makes sense. So we basically have a static lock that's shared among all the async functions, is what it's doing here. Here we have thread parameters. Don't need this anymore. These are basically the ways in which we're going to interact with the thread. Although, honestly, I'm not using bstop right now. I could. It would involve changing the methods I'm invoking so that I could pass a stop value into them and then have it be like able to be terminated that way. But I haven't done it yet. So like it actually is something I should do, because right now you could crash it if you stopped it while it was running. You would have to basically wait for them to finish and then you stop it. It's fine. If they're still generating and you stop it, you're probably going to crash right now. I haven't tested it though. So yeah, okay, so we got our bulk insert task. These are thread controllers. They're going to be the same between all the different multi-threaded things. We have our parent node, our reference node, our reference point cloud, our reference depth, and our reference randomization bounds, and our reference activated. And those will all be set in the constructor here. This is the header file, so that's implemented over here, but I'm going to step through this file first. So our constructor takes all that shit, and it also takes a promise. That's how we're going to return our data when it's done. We have init, start, run, stop, exit. We don't do any of these. These are all, okay. So these do what I just typed in comments. Doop, doop. starts the thread, so you can make a new one. In the video I watched, they were starting the thread in the constructor of the thread, but in debugging, I needed the ability to kind of look at when the thread was starting and when it wasn't starting and have a little bit better control over that, so I put that logic in a start call. The rest are just automatically managed by the execution of the frunnable. You don't have to specifically do anything other in the header other than just declare that you're gonna implement them. Clean all this up. So this is find at depth. This takes a reference node and a reference depth, and it will find all the nodes that are descendants of the past node at the given depth from that node. So yeah, that's how that works. Yep, so we construct it the same way. We have our values that we pass in and get initialized, and we have our promise that we're using to return data. Again, I'm going to just go ahead and copy this. These will all be the same. Okay. Find in depth is the same thing as find at depth, except instead of only looking at the leaf nodes at the depth that was given, it will give any activated nodes that it finds, including the parent, between the parent and the child. So if I say, hey, give me your children, find in depth 10 levels deep, then it will return itself if it's activated, and then any activated children between it and 10 levels deep. That's how that one works. So these headers look good. Satisfied with my review of them. Come up here and check the implementation. Standard constructor destructor for the async module itself. Then we have, okay, book insert task constructor. We set all our gotta get used to C++ terminology, right? I set all our member variables to the values passed in. Start just basically initializes our thread object and passes our self and the name of the operation. Destructor kills and deletes the thread. Exit deletes the promise. Stop flips bstop to true, although admittedly this isn't doing anything right now. I need to change this method to take a boolean to like stop it short, and then I could. And then the run method right locks the thread and does the actual logic. We declare return nodes. Seems like I don't need this. And this is why I stepped through the code line by line. So this is just the same thing as it was already doing. I just had an extra line of vestigial code in there. Stop stops the bstop. Makes sense. Again, I'm not hooking into this, but it's something that I'll want to hook into. In fact, I might do that next after I do this review, and just make it so that I can utilize this better. Async find at depth, reference, depth, promise. Again, setting my member variables. All of this thread lifecycle shit is always the same. Everything except the run method, pretty much always the same. I realize that this is the same as doing auto, but it's like more readable to be explicit, I think, with what you're getting. Now I have to rely on like code completion to show it to me. But auto's good for like banging out code. Like if you don't want to worry about the type, just use auto, and you can get the code up and running, and then you can go back through and replace all the types. Same boilerplate shit. Consistent naming conventions across all these methods. All right, great. That's it. So I've reviewed the async methods. So now I got to do that for every other one of these files. Just a last sweep to make sure everything makes sense. Clean up any code that I may have put in place that I ended up not using. So here we have our family structure, parent and children. We have our non-recursive data. This is things like your bounding box, your center point, your size, your depth in the tree, your seed, your path, your randomized values. We can actually remove this because we ended up locking outside of this. So like I ended up these not needing to be thread safe. Perfect. This is where fucking like Copilot is actually good. It's like it's writing my comments for me. I don't want it for the code most of the time because most of the time it's wrong. But like, hey, save me from writing half that comment. That's great. Okay, so these are our helper functions that we basically are being accessed from our Proctree wrapper, and they do the things they say they do. I wonder. I'm trying to. I had an idea just crop up in my head. Like if I had the node that, like, say I pass a point like the user's location, and I get the leaf node that the user's in. I could probably write a function here to crawl back up the tree and give me the nearest neighbors from every level of the tree relative to its size. And that would be the best way to do it. Because then I get all the galaxies near me in the galaxy coordinate space frame of reference. I get all the stellar clusters in the stellar cluster frame of reference. I feel like that's the way. So that'll be a method that I'll have to write soon. So yeah, we got our book insert in our finds. This is where the meat is. We basically always want children to have eight members. So I'm just statically instantiating it to 8 null pointers here, and I think there's a shorthand for this. I just don't know what it is. Actually, we can ask ChatGPT. The array. This is why. Hang on. This is why you can't trust anything this thing says. You always have to like have your brain engaged when you deal with it, because this is bullshit right here. It doesn't like. That's better. No thanks. I think I'll just leave it the way it is. Okay. Insert node by path. Path, bounds, activate. Current node, it gets itself. Reference to itself. It scoots up to the point at which it gets the root. Finds the length of the path that's being processed. If the path is only length 1, that means that it's the root index, or we can assume it is. Return the current node. Next we iterate the path length starting at 1, which is our root. This was interesting. I didn't realize this is how you did this in C++, but it's just fucking subtracting the ASCII values. And I guess I never connected that it worked that way, but it does. So whatever the ASCII value for 0 is the start of the integer ASCII values. So basically, if you have an ASCII value of 0 and you subtract an ASCII value of 0 from it, you get 0 as an actual number. And if you have an ASCII value of 1 and you subtract the ASCII value of 0 from it, you get 1 as an actual number. That was interesting to me. So like this is basically a cast string to int, basically. Or cast char to int. So we flag activated as if we're at the end of our path. And then finally we inject a node into the index we calculated and flagged activated based on our activation calculation. Because we're inserting by path and not by a point, there's no location offset. And we pass in randomization bounds. That helps it randomize its values when it gets to the bottom. It's actually used by a creator update. Okay, that one looks good to me. Start node by point in depth. Point depth randomization bounds activate. If the depth is 0, we return the node. Is this a recursive function? Yes. Okay, so it's a recursive function where we're basically decrementing the depth as we recurse down the tree. And that's why it has our termination function, which is when depth is 0, we return the current node. Normalize point, node data center, divided by node data size. Okay, so we don't have a local offset until we hit the depth at which we want to inject the actual activated node. And that node will have a local offset based on the point that was inserted, and that offset is calculated by subtracting the center from the point and dividing it by the size, which is, the size is an extent, so it's actually half the total width. So that gets our normalized point, and then we invoke creator update node by index one more time with the activated flag The randomization bounds, the normalized point, we just calculated the node data index. Looks good. Else, my comments pretty much say what it's doing. Octant index, so the function they're doing there is basically calculating the there's a, so you can think of the octants, right? There's 8 of them. So if you're in binary and you wanted to represent each octant, and you wanted to do it such that when you're positive on the x, y, and z axes, you're at 1, 1, 1, and when you're negative on the x, y, and z axes, you're at 0, 0, 0. You could represent that in binary. You could represent each of those octants as binary representations of their relation to the axis. All this is doing is taking those relations and turning them back into like an integer index. So this is our recursion function. Assuming that we are not terminated at the end of our depth yet, then that means we need to go down a layer, which means we need to calculate our offset from the point that was inserted and which octant it falls into. We need to make a new child. And then we need to invoke insert node by point in depth on the new child. We'll get to this. Basically, this takes in your point. This is the same function. I mean, we'll get to this. This takes in your index, your offset, your bounds, and if you're activated or not, and will either create a new node in the child index, or if a node already exists, it will cluster with it. Insert node by normalized point in depth is the exact same thing as insert node by point in depth, except it normalizes the point based on the node size and node center into its local coordinate space. That's it. That's the only difference. And then it just invokes insert node by point in depth, which is the recursive function we just looked at. Seems fine. Same shit here. You would think this would be more complicated, but it's actually not, because we're just invoking. Okay, we don't need this comment. Right, this comment. We're just invoking insert nodes by normalized point in depth over and over and over and over for however many points we've got, and then returning the result set. Find nodes at depth from node. It takes a depth in a node. Checks to see if the node is activated and has the desired depth. This is our recursive termination function. It checks to see if the child is there or not. If it's not null, it recurses down the tree, invokes the same method here, and appends the result. And I guess I could probably actually just append, like straight up pin the output of this call. I'm real nervous about breaking shit right now too, but I think that should work. Basically trying to avoid assignments if possible to speed it up as much as possible. So like if I can get away with not allocating a variable, I mean, I'm already allocating a variable inside of here, so it's probably not that big of a deal. No, it probably is kind of a big deal. If I can get away with just, like, the less assignments, the better. Okay, so see if this shit still works. good. Bulk insert still churning nicely. Looks fine to me, right? Looks fine to me. Find in depth is very similar to the other one. It's actually less simple. I mean, less complicated. So we don't have to check if we're at the maximum depth. That's the only difference. Okay, the child, we check it. Looks good. Looks good. Alright, now the monster. This is actually the most complicated method in the class. The rest are pretty simple. It's create or update node by index. It takes an index, a location offset, a randomization bounds, and whether or not to activate the node. Checks to see if there's already a child at the index. If there isn't, we make a new child. We calculate all its derived tree values, like this. So path, index, depth, size, center, bounding box, seed, parent. We set its parent as ourself. We set our child at that index to the node we just created. And then we go ahead and externally, outside of here, snag a reference to it. And the reason we do this is because if we didn't hit this if block, this new node value would not be instantiated outside of this block. So I can't use that. So basically this has gone in here, and then we've gotten it back out of here again, or this was not null to begin with, and so we just snagged this node, right? Next. Checking activation status. So if we're activated, that means we're basically flipping this node on, right? So we snag a random stream from the seed because we're going to need it. We set our location offset. Like, we don't do that calculation here. It's expected to be done already by this point. We get our nodes type from the randomization bounds. It's one of the properties of this struct. We set our relative scale to a random float in range of our min relative and max relative scale. Set our density to a min and max density from the same structure. Our temperature, min and max temperature. Our composition, min and max composition. All makes sense. Okay. The node is already activated. So if the node is not activated, if the node was activated, but it was not already activated, so these are all just setting up temporary values right here. If the node was already activated, or already not activated, then this block won't fire, and we just set our values to the values that were calculated. However, this I can delete. This works now. However, if the node is already activated, this is where the clustering logic comes in. So the way I'm handling that right now, and to be fair, I should be using the volume rather than just the half radius, or the half diameter or whatever. But for now, I combine their scale and take the min of 1 and the scale. This means that if they're, say they're in like 0.05, 0.1, 0.2, then you haven't hit the maximum size for the node, so you would just be at 0.35. But say they were 0.3, 0.3, 0.3, 0.3. Well, that would be 1.2. It's greater than 1. can't be greater than 1. That's the size of the node that you're in. So we go ahead and set your scale to 1. And what's cool is the rest of these are calculated with a weighted average of the existing node's node data times the existing node's relative scale plus the temporary values density times its relative scale divided by the combined scale. So what's the effective result of this? If I insert 100 nodes in 100 points into the same node, after the node hits 1, the largest size it can be, the density, temperature, and composition values all start going up. That's it. So it kind of works like reality, like where if you cram a bunch of shit into a single space, it gets denser and hotter. That's it. Finally, we set up all these values so that we can finally set up our proceduralized values and then return the new child that was inserted. And that's how that node works. So all this looks good to me. I think I'm probably going to stop there for the night because I'm pretty sleepy. I've been face smashing on this problem for a while now. So I'm happy to have it done, but at the same time, I am kind of tired of looking at it. And it works. Pretty cool. So I've reviewed these two. I still need to review. Okay, this is none needed. This is literally nothing. It just initializes a new tree and returns it. Okay, that's auto-generated. Most of the rest of these aren't a big deal, except for these wrapper classes. So, like, actually just went over the majority of it. These are okay. Those make sense. Probably maybe not as a plugin if I ever release it, but I'd have to figure out another solution in that case. These are all my defaults. This is the randomization bounds. This is used for proceduralization bounding, and this is our node data. This contains all the information about our node that is not recursive and is actually an f-struct, because like we can make these off the game thread. We just can't make U objects. So we store all our like discrete math information about the node in a struct that's visible to Unreal. And we keep all our parent hierarchy in a structure that isn't. And then whenever you ask for a parent, we just wrap it. Proctree structures is just some data functions that we got. So we got our node data and our randomization bounds that are typing them. Oh, excuse me. Factory just builds our tree. Plugin is auto-generated. Okay. So I ended up having to also put this structure in. This is a struct that's used for the returns from my search functions. It gives the reference node that was passed in to trigger the search, the result nodes that were found as a part of the search, and the depth that the search was executed at. It just allowed me to get by with only returning one value. You can return more, but it's a pain in the ass to write those things, so. And I didn't want to refactor everything after I had it all working. So this is our node wrapper. It gives us the ability to get the child as a wrapper, or get the parent as a wrapper, get the child as a wrapper, get the children array as an array of wrappers, or get the node data, the struct that we were talking about, that was a blueprint type struct. It also gives us blueprint callable methods for all the insert methods that we were just looking at, except for bulk. You can't do bulk on this. It gives us the ability to get the internal node but not expose the blueprint, so this is used in the C++ code. And it gives us the ability to set the internal node, again, not exposed to blueprint, it's in the C++. And then we have our internal node. Okay, that's that thing. This is the tree wrapper itself. You initialize the tree with a size and a depth. The tree has the ability to get the root. It has the ability to insert, to bulk insert into a node some points at some depth with these bounds and activate it or not. So you could build out a bunch of empty space. I don't know why you would do that. Maybe activated is not necessary to pass in, and we just assume that anything that's being inserted at a given level is activated. But anyway, it's kind of whatever. Find nodes at depth, find nodes in depth. We contain an internal root node. Values to define our maximum depth and our leaf size multiplier and our leaf base size, although these all get set in the initialization logic. And then we have our multicast delegates. These are tree level multicast delegates that we can bind events to in blueprints to basically respond when a bulk insert is finished or a find is finished. We just do some cleanup here. I think I can actually just do this too. It is working. So before I go deleting all the thises in the project, I would like to finish just reviewing the functioning code. Insert node by path. These are just invoking methods on the nodes, so they're not very beefy. Internal node gives the node, set internal node, sets the node, all pretty clear stuff. Clears the tree. Initializes all my root values. Returns the root, or actually returns a wrapper containing the root. Okay, so that's a to-do. Now that I understand how the code works out a little bit better, so, like, rather than having to call this fucking bullshit, I could just have the constructor take it in, which would be better, I think. Just a minor improvement. All right. So back to this. Here's our async, our actual async functions. I actually reviewed these earlier, huh? A little bit at the start of the stream. So we're using promise future framework. I can construct my task up here because I don't start it to here. This is the code that happens when it finishes. We basically broadcast the resulting data. Same shit pretty much in all of these. I mean, like, we're like, it's not crazy complex because we're just invoking other methods, right? Like, we're going through here and we're invoking the async wrapper that we made. That's doing all the stuff we just looked at it doing and returning us a set of results, and then we're constructing a response, our result wrapper, and returning that data back to the blueprint via an event. And that's pretty much it. So I think coming up, maybe tomorrow, maybe later, I'm gonna try to integrate this into the project where I have the other like blueprint built Proctree, and see if I can't start trying to build like a proceduralization harness around this thing, just to get like some verification that things are working properly and whatnot. I'm not 100% sure about some of the math, because before, like when I built this before, where did it fucking go? When I built this before, I forced these to be -1 and 1, which changed the way all the math worked into something that seemed simpler at the time. But it seems like maybe this way was more simple after all. But I'm curious because I haven't verified like visually that these nodes are getting generated in the right places, right? It just like the data looks correct. It looks like randomly distributed octree data. So I still got to test that. And that's coming up too. Anyway, I think that's going to be it for this one.